Welcome back. Did you figure it out? Let's talk about it. So, here's what we know. Typically oldest layers are at the bottom. Okay, well, I've got two layers at the bottom. I got B is down at the bottom. A is kind of at the bottom too. Both of them are down here, excuse me. So which one is older? Well, remember, in order for me to break through a window, that window has to exist first. So A looks like some sort of material that kind of cut up through. So in order for A to kind of cut through B, cut through C, and cut into D, maybe those things had to exist first. So I'm pretty much going to ignore A for now, and I'm going to say B is the oldest, then C, then D. Now I have A and E left. Let's just verify. Let's make sure B, C, D are correct. Another thing about A, it looked like it was hot rock because it created this zone of contact metamorphism when it came in contact with B, C, and D. In order for something to be burnt or metamorphosed, it had to exist first. So B, C, and D had to exist first. Okay, so I'm on the right path. So B, C, D, then I'm going to say A came next, cut through, and then E looks like additional sedimentary rock layer that was put on top. So that's probably correct. However, you can also say B, C, D, E, A, because we don't have enough information as what's given to be definitive in knowing what came first, A or E. Maybe B, C, D, E, all of those looks like sedimentary rock layers formed, and then A started to cut through. It didn't make it all the way to E, it just stopped, but it's still, so that makes it younger, so in that case B, C, D, E, A, or maybe it was these three sedimentary layers, B, C, D, A cut through, and then all of a sudden, sometime after that, the layer of sedimentary rock E got piled on top. That's what we got. All right, but you're still telling a story. You're able to recreate the past, how geology occurred, just by looking at kind of layers and strata of rock. All right. So, what we just did is something called stratigraphy, which is the science of rock layers and the processes by which strata layers are formed. There are principles of stratigraphy that helps us figure out kind of the geology of the past based on some rules. These rules were developed in the 17th to the 19th century, so the 1600s to the 1800s, based on the work of Nicholas Steno, James Hutton, my main man Will Smith, among others. All of those were mentioned back in Unit 1. And there are 6 main principles of stratigraphy, 6 rules. And if we follow these rules, we can recreate the geologic past just by looking at the layers or strata of rock. The first principle is the principle of superposition, meaning the oldest layers are at the bottom, the youngest layers are at the top. So if I were to compare two layers, B and D, which one's older? B. Why? Because it's at the bottom. Which one's younger? E. Why? Because it's at the top. Right? So same thing in reality, the oldest layers are typically at the bottom, youngest layers are on top. Sometimes weird things happen, but this is typically what occurs. The next principle is the principle of cross-cutting. Layers of rock must be older than any feature that cuts or disrupts it. So looking over, let me get rid of this one. Okay, so looking at this rock, so this black rock, it looks like it has some white stuff that's cutting through it, and as well as kind of a thin black line cutting through it. Well, that means the rock has to be older, because it has to exist first for this stuff to cut through. Now, what came next? Well, the white stuff is younger than the black stuff, it's younger than the rock, but the black rock is the youngest. Why is that the youngest? Why is that the last thing that happened, the most recent thing to happen? Because not only does it cut through the old rock layer, but it cuts through that white layer as well. So both the rock and the white layer of rock had to be there before that black material cut through. What about over here? So we have all of these layers of, looks like sedimentary rock, but then this actually fault cutting through here. What type of fault is it? Hanging wall. Seem to have, looks like the hanging wall dropped, looking at this layer, that layer here. What type? What? Hanging wall dropping? normal fault. In any case, these rock layers are older. This feature must be younger because this fault cuts through these layers. So the layers existed first, then there was the break. All right, so it's the principle of cross-cutting. The principle of lateral continuity, fancy terms. Sediments are deposited in continuous layers. So here's the Grand Canyon. This side of the Colorado River, sedimentary rocks. This side of the river, sedimentary rocks. So, did they form just kind of on their own in these two like weird stacks of sedimentary rocks? No, they formed continuous layers. You can see how this layer of sedimentary rock is the same material as this layer of sedimentary rock. This layer of sedimentary rock is the same as this layer of sedimentary rock. So they formed a continuous layer of rock. This river had to cut through and cut down through them. So that disrupting that came later. So it's kind of like the principle of cross-cutting. But we do know that stating the principle of lateral continuity, these were once one continuous layer. All right, again, we can kind of match everything up here. Another principle is the principle of original horizontality. All sedimentary rocks are originally deposited as horizontal sediment. If I had a pile of dirt and I let it go on my desk, it would flatten out. That's how gravity works. So as sediment is deposited, it settles in horizontal layers. Those material is compacted and cemented together to form sedimentary rock. In any case, that original material is deposited horizontally. Sediment can't be deposited on an angle. If I were to dump a bunch of dirt or sand on my arm, it would just roll off to the flat table and then be horizontal. So sedimentary layers aren't angled. They're always horizontal. If we do see them tilted, well, that came afterwards. Some process tilted those layers of rock afterwards. The principle of inclusions. Rock fragments, for instance, like this one here, must be older than the rock containing the fragment. So this had to exist first, so it's older, while the surrounding rock is younger. Same thing here. This rock fragment is contained within this younger rock material. A lot of the times this happens with igneous rocks. So you have some sort of old rock underground falling into hot magma. That magma cools and solidifies to become a rock, but there was already an existing rock in there as the magma was cooling. So the principle of inclusion says rock fragments are older than the rocks that contain them. And then we have the principle of faunal succession. This has to deal with fossils. So fossil groups were succeeded by other fossil groups through time. It's pretty uniform. There are certain fossils we use to kind of give an age range to rocks, a geologic age. Different fossils of organisms. These organisms only existed for X certain amount of time, so we can use certain fossils to kind of indicate layers of rocks and kind of tell us how old rocks are. Like, for instance, we won't find trilobite fossils mixed in with coral fossils. These are going to be different layers. So throughout Earth's history, different organisms which died to create fossils will be found in a particular order. So typically, older ones are at the bottom, the younger fossils are at the top. So those are the 6 principles of stratigraphy. Now, sometimes weird things happen. Those weird things are called unconformities. Unconformities, again, I briefly described them, but they're gaps in the geologic record. They're gaps in time. They may indicate episodes of crustal deformation, so crumpling of the crust, folding of crust, erosion, the breaking down of movement of material, and or sea level variations, new deposits of sediment and or sedimentary rocks. So sometimes weird things happen, and we call them unconformities. They can represent time when deposition of sediment stopped, where weathering and erosion occurred, removing some of the previously deposited rock, and finally deposition was resumed. So not only it might be something that's there, it might be something that's not there. It might be something we see, or something missing, something we don't see. So there's 3 types of unconformities. The first is called a disconformity. This is a weird one. It's kind of a hard one. There's an erosional surface, so missing material. There's an erosional surface between 2 horizontal sedimentary rock layers. So I have a sedimentary rock layer here, another one down here. They're most likely both sandstone, but you can tell one's a little bit different color. So these are two different types of rocks. But between those two would be a disconformity. So we have sedimentary rock layer here, and we have a gap in time. Now the only way we can figure out we have a gap in time is if we were to maybe find some fossils in these different types of rocks. So a disconformity can be hard to recognize in the real world. Again, fossils would help with that. Oh, I have one fossil, I skipped some other ones, and now I have these other fossils in the layer above. There's a gap in time. Something's missing. There was nothing deposited, or there was stuff here and it got ripped away. It eroded away. So missing time, missing information between two sedimentary layers is a disconformity. A nonconformity occurs when you have typically younger sedimentary rocks in contact with older igneous or metamorphic rocks. So this again is the Grand Canyon. Above this line are all sedimentary rocks. See these kind of layered rocks. It's a good indication of sedimentary rocks. Below those, in fact in the Grand Canyon, at the basement of the Grand Canyon in this area, those are metamorphic rocks. These two rocks form via different processes. Therefore, something weird happened to have these two different types of rocks. Therefore, since there was a change in process of how rocks are created, that's a nonconformity. Something weird happened. So you have sedimentary rocks kind of sitting on metamorphic or igneous rocks. In this case, these are metamorphic rocks. And then probably the easiest to recognize, and I showed you this picture earlier, is an angular unconformity. This is when there's some sort of erosional surface, so missing material, between younger horizontal rocks on top and tilted sedimentary rocks below. So you can see these rocks below have been folded and tilted up. There's some material that's been weathered and eroded away, broken down and missing, and then on top of that, horizontal rocks now exist. So a different process that formed this material on the bottom is different than the process that formed this material on top. So that's weird. That's a change in kind of process. Therefore, we have an unconformity, in this case, an angular unconformity. So how that kind of works in a diagram, so you have some original sedimentary rocks, original horizontality, they're laid down horizontal, oldest at the bottom, youngest at top. Some sort of deformation, maybe some sort of convergent boundary, maybe plates crashing together, folded up the material. Weathering and erosion, water, and weather and rain broke down the rock, kind of the top part of the rock, kind of just ground it right off. On top of that were new sedimentary rocks being deposited. So you have horizontal sedimentary rocks on top and then tilted sedimentary rocks below. It's an angular unconformity. One of those exists at the bottom, towards the bottom of the Grand Canyon. Again, horizontal sedimentary rocks, angled rocks below. So angled below, flat, horizontal on top. That's an angular unconformity. In fact, there's a few unconformities. There's some disconformities. That's gaps in time between sedimentary layers. A nonconformity, we have metamorphic and igneous material below sedimentary rocks. So we get all three in the Grand Canyon. But this angular unconformity is a special one called the Great Unconformity. It's actually a dramatic boundary which represents a huge gap in the rock record and our understanding of Earth's history, because that missing information is worldwide. Something weird was going on. We just have a big gap in time. In some areas of Earth, 100 million years are missing. In other areas, up to 1 billion years of rock information is missing, kind of just depending on your location. And this great unconformity was named in 1869 by John Wesley Powell, explorer, geologist, Arizona, infamous Arizonian early on during his first documented trip through the Grand Canyon. He was the first to go through the Grand Canyon down the Colorado River in a wooden boat in the 1800s. Knowing all of that, knowing the principles of stratigraphy, different rock layers, types of unconformities, you can now look at something like this and put it together. Fun, isn't it? We'll save something like this for lab. We'll pause here. That brings an end to relative age. When we come back, we'll talk about geologic age. See you back here in just a minute.